So last class we introduced the electrical field that's produced by an electrical charge. It's a new abstract concept. This class we're going to introduce the electrical flux that's produced by an electrical charge. It's another new abstract concept. They're related concepts. They're different ways of thinking about electricity. Sometimes it's better to think about the electrical field. Sometimes it's better to think about the electrical flux. But they're kind of tools in the toolbox of electricity. So specifically today, I wanted to introduce the concept and quantitatively define electric flux. I wanted to talk about the flux law. We call it Gauss's flux law, in which charges are what I call sources and sinks of flux. I'll describe that later. And then we're going to, as we go through today's class, we'll look at some examples of calculating fluxes, calculating fields using flux laws, and so on. Okay, so first part, I'm going to introduce concept of electrical flux and define mathematically electrical flux. And I'm going to do that in relation to the electrical field. I'm going to connect it to the electrical field. Oops. Okay, so to introduce the concept of electrical flux, I wanted to draw an analogy with more concrete water flux. Electrical flux is like electrical flow, and water flux is water flow. So I want to draw that analogy as to make this abstract electrical flux a little more concrete. So that's what's on this slide. So after the washing up last night, I took this picture of my sink at home, and I'm going to compare this picture of water flux with this sketch over here, which is of an electrical field due to an arrangement of charges. And we'll see they're quite similar. And so it's a way of thinking about flux in concrete terms. So let's look at the water. Here's the faucet, and into the sink, it's into here. This region here is out of the faucet is a source of water. Okay, and then the drain here. This is where the water vanishes. So the water's coming in from the faucet and vanishing down the drain, and we see a pattern of the water flow from what I'm going to now call not the faucet, the source, to what I'm now not going to call the drain, I'm going to call it the sink. And so we can think of the flow of water, the flux of water, as it flows from the source to the sink. We can think of the electrical field in a similar way. We can think of this positive charge as the source of field lines that flow out of this positive charge. So this is like the faucet. And we can think of this negative charge as the drain of the electrical field lines. The field lines, or the electrical field, is draining into the negative charge. And so this plays the role of the drain. And so just like we can watch the flow of water here and think of the concept of the flux, the flow of water, we can watch the flow of electrical field here and think of a corresponding concept of electrical flux. So that's the basic idea. Now, there's an important difference when you think about electrical field of arrangements of charges and electrical flux produced by arrangement of charges. And that important difference has to do with when we think about a field. If I quote a field, if I tell you a field, I'll be telling you a field at a given point, location in space. when I think about flux, when I tell you a flux, it's a flux through a surface, not a point, a surface in space. So I'm trying to picture that on this slide here. So again, here's the electrical field of an electrical dipole with a positive and negative charge. Here, in magenta, I'm indicating the electrical field at a particular point. So it's a vector, and I'm indicating its direction and its magnitude. So that's the electrical field. And then down here with this new symbol phi, that's going to mean electrical flux, I'm indicating the electrical flux, not a point, but through this surface. So this is a surface, a two-dimensional surface, and I'm indicating the flux through that surface. So when you look at field lines, when you look at a sketch of an electrical field through field lines, the density of the field lines, how tightly or loosely they're packed, tells you the strength of the electrical field E. When you look at the field lines, if you count the number that are passing through a surface, it may be a large number passing through the surface, small number passing through a surface, I think 3 passing through this surface, that's telling you the flux through the surface. It's in proportion to the number of field lines. So when you look at a sketch of electrical field lines, you can read that sketch for both the electrical field at a given point in terms of the density, the closeness, or how closely packed the field lines are, and the flux, how many field lines go through a surface. So that's how we visualize flux and field. This is how we mathematically define electrical flux phi in terms of the electrical field E. So let's just go through this slide a little bit, and then we'll look at some examples of this slide. So in this slide, in tangerine here, we've got an electrical field. And I'm drawing the field lines. They're sweeping from the left to the right, and I'm denoting it E here. And this happens to be a uniform electrical field. The field lines are equally spaced, same direction everywhere. Also in this picture, I'm showing a surface that is immersed in that electrical field, this sort of tan-colored surface here. I'm representing mathematically that surface with that magenta vector A. So the length of this and the direction of this arrow represents the vector A that describes the surface. So the length of this vector describes the area of the surface. So if it was a greater area surface, it would be a longer vector. If it's a smaller surface, it would be a shorter vector. The orientation of that vector A describes the orientation of the surface. That vector A, if you see in the sketch, is at right angles, perpendicular, 90 degrees to the surface. So E and A describe the electrical field and the surface, and they're the two ingredients that determine the flux through the surface. So the flux through the surface, a couple of ways you can write the equation for it. That flux phi through the surface is equal to the product of the perpendicular piece of the electrical field. That's what this little perpendicular sign means, times the area. So if you were to determine the perpendicular to the surface component of the electrical field and multiply it by the area of the surface, that gives you the flux. Or alternatively, this little equation here says that the flux can also be written as the magnitude of the field times the magnitude of the surface times the cosine of the angle between the electrical field vector and the area vector. And so that's a second way that we often write the electric flux. As I say, if you want to visualize the electrical flux, just imagine it as reflecting the number of field lines that pass through the surface. So the more field lines you've got, that's a bigger flux. The less field lines through the surface, that's a smaller flux. Let's make this a little more concrete. And I've got this slide and two more slides that I'm going to go through fairly quickly, but they're just quick examples of how the flux depends on the field, it depends on the surface, and it actually depends on the orientation of the surface in the field. And that equation, phi equals Ea cosine theta, encodes the dependence on the field, on the surface, and the orientation, the relative orientation of field and surface. So let's see how all that works. On this sketch, I'm illustrating the dependence of the flux on the surface area. So on this sketch, I've got a uniform electrical field. It's 50 newtons per coulomb everywhere in this region of space. The field lines are equally spaced. The field lines are in the same direction. It's uniform field. I got three surfaces, one on the left, one in the center, one on the right. They have different sizes. The one on the left is large, the one on the right is small, and the one in the center is intermediate. So this is 10 square meters, 1 square meter, and 1/10 of a square meter. These surfaces are orientated such that the field is perpendicular to the faces of those surfaces, which actually means that the field and the vector A are parallel to one another. So this is a special orientation of these surfaces in the fields, in which the field lines are perpendicular to the face of the surfaces, in which the vectors E and A are parallel to one another. So in that case, the flux, for this orientation, the flux through each of these surfaces is just the field times the area. Field times the area. The perpendicular component of the field times the area. And so all I've got to do is multiply, since this field is perpendicular, the 50 newtons per coulomb times the three areas. And so these would be the three fluxes. You see, this area, this surface is in the same field as this surface, but because this one is bigger, this has a large flux. This one is smaller, it has a small flux. And so flux depends on the surface that you're thinking about. It depends, in this case, on the size of the surface that you're thinking about. Flux also depends on the field. So in this example here, I'm showing you the field dependence of the flux. So in this particular sketch, I've got three surfaces again. You see them in cross-section here. They all have the same orientation. It's perpendicular to the field. And they're all the same size. In this case, they're all 1 square meter. What's different in this case is that over here on the left, this region of field is strong. It's 15 newtons per coulomb. Over here on the right, this region of field is weak. It's only 5 newtons per coulomb. And this region in the center is in between those two. It's 10 newtons per coulomb. You can see it from the density of the field lines, how closely packed the field lines are. So here the field lines are closely packed. That's a strong field. Here they're weakly packed. That's a weak field. Here it's intermediate. So that's an intermediate strength field. Again, in this case, the field lines are perpendicular to the faces of these surfaces, which means that the field vector E and the area vector A are actually parallel to one another. In that case, the flux through the surface is just equal to the electrical field strength times the area of the surface. And so here I am calculating the three fluxes in these cases. The areas are the same in each case, but what's different is that the field over here is strong, the field in the center is intermediate, the field on the right, that's weak. And so when I multiply the different field strengths, 15, 10, and 5 newtons per coulomb, times the areas of 1 square meter in each case, I get different fluxes. This is a large flux because there's a strong field here. This is a small flux because there's a weak field here. You can see there's more field lines passing through the surface here, less passing through the surface here. So that corresponds to a large flux here, a smaller flux here. Finally, not only does the flux depend on the field strength, depend on this surface size, it depends on the orientation of the surface within the field, or the field over the surface, the relative orientations of those two things, E and A. So look at this example. In this example, the field is the same everywhere. It's a uniform field. The areas of the surfaces are the same everywhere. They're all 1 square meter. So that's different from the last two examples. In one case, I was changing the area. In the other case, I was changing the field. Now I've got same area, same field. What I've got that's different in the left, right, and center is the orientation of the surface in the field, the relative orientation of E and A. So in this picture on the left, the area vector A is in the direction of the field vector E. So here they're parallel. There's an angle of 0 degrees between E and A. In this one in the center, the area vector for the surface, which is perpendicular to the surface, is at 90 degrees to the electrical field vector. So E, A are perpendicular. And then this final case here, there's some orientation of the surface that's in between parallel and perpendicular is 30 degrees. There's a 30-degree angle between the vector A and the electrical field vector E. And these three surfaces, which are the same size and the same field, have different fluxes through them because they have different orientations in that electrical field. So here we need to use this full equation for the calculation of the flux. It's the size of the field times the area of the surface times the cosine of the angle between the E vector's direction and the A vector's direction. And so that's the cosine of these angles here. So we're going to get different fluxes here, not because the field's different, not because the areas are different, but because the orientations are different. In this case here, where they're parallel, I get the maximum flux through this surface. In this case here, where they're perpendicular, there's actually no flux through this surface. Although it's in a field, there's no flux through that surface. And in this case here, where we've got 30 degrees, it's intermediate between this maximum flux and this 0 flux here. You can see it on the picture. Again, think about flux visually as being the number of field lines passing through the surface. A lot of these field lines pass through this surface. You know, there's 1, 2, 3, 4, 5, 6, 7. This surface here is in between these field lines. None actually pass through it from one side to the other. So this has 0 flux. And then this is intermediate. This is somewhere between. We got 1, 2, 3, 4, 5, 6. Somewhere between these two extreme fluxes of 0 or maximum. Okay, so that's to introduce you to this new idea of electrical flux and how it's related to electrical field, how flux is related to surfaces, fields you quote at points. Here's one little demonstration of electrical flux. So in this case, I've got an electrical field indicated by the field lines in these little arrows here. And I've got two surfaces in this field. I got this vertical surface that's on your right, and I got this angled surface that's on your left. Now the surfaces have different areas. This one's bigger, the angled one's bigger, the vertical one smaller area. But they actually have the same flux through them. The same number of field lines are passing through the vertical surface and the angled surface. They have the same flux, electric flux, through the vertical and the angled surface. And so that's an example that in calculating electrical flux, what matters is the strength of the field. What matters is the area of the surface. These areas are different. But what also matters is the relative orientation of the field and the surface in the field. And that's different here too for the two surfaces. And those two things, the different areas and the different orientations, compensate one another. And these two surfaces have equal flux through them. Okay, so I want to look at an example calculation of an electrical flux. So what we're going to imagine is we've got a uniform electrical field, 500 newtons per coulomb, uniform electrical field. I pictured it here in red. These are the field lines, as many as I could draw. In that uniform field, we placed a cube that is 1 centimeter by 1 centimeter by 1 centimeter. Here it is, in blue. And the question is, what is the total flux through that cube of electric field? So what is the electrical flux, what we might call the net electrical flux, through all the faces of that cube? This introduces an important point when we talk about electrical fluxes through surfaces. We're going to talk about closed surfaces and open surfaces. So as an example of a closed surface, think about the surface, the full surface of this box. So there's the top, there's the bottom, there's the left, right, front, and back. Right? If you've got a closed surface, if you're outside the closed surface, I'm outside the closed surface, then I can't get inside the closed surface because I'd have to go through a wall of that surface. So that's what we mean by a closed surface. We mean a closed surface is that there's a real distinction between inside and outside. You couldn't get inside if you're outside without punching through that closed surface. You couldn't get outside if you're inside without passing through that surface. So that's a closed surface. The lid of the box, that's an open surface. Right? If I'm on this side of that open surface, the lid of the box, I can get to the other side of that surface just by walking around. So that's what we call an open surface. So we're going to be distinguishing between open and closed surfaces when we talk about fluxes through surfaces. And this cube here is a closed surface. If you're inside that cube, you can't get out to the outside region without passing through its walls. If you're outside, you can't get inside without passing through its walls. Okay, so I want to calculate the flux through that. I think I'm going to do this on the document camera. Okay, so I started this here. We're going to calculate the flux, the electric flux through this cube. Remember, it's 1 centimeter by 1 centimeter by 1 centimeter. In this field that's 500 newtons per coulomb, and it's pointing in the positive x direction. And so we want to calculate the total flux, the net flux through the cube. How am I going to do that? First thing is that I'm going to do it in steps. So I'm actually going to, I recognize, right, a cube has 6 faces to it. It has a top, a bottom, a left, a right, a front, and a back. And I'm going to calculate the fluxes through each of the 6 faces. Flux through the top, flux through the bottom, so on and so forth. Then, Once I've calculated the flux through each face, I can figure out the net or total flux through the cube by adding those numbers up, adding the 6 fluxes up. And so that's the way I'm going to calculate the total flux through this cube. Let's start. Let's start by calculating the flux through the top. So here's the top face. So what's the flux through that top face? Well, it might help if I sketch 2 vectors that are involved in the flux. So there's the electrical field vector, and that's from left to right in the positive x direction. And for the top face, the vector A that represents the top face, that's vertically upwards. And so those are the 2 vectors that are involved. And I can see from my little sketch here that in this case, the vector A representing the top surface and the vector E representing the field are at right angles to one another. So if we think to our definition of flux, flux is phi. It's the size of the field, magnitude of the field, times the size of the surface, area of the surface, times the cosine of the angle between the field vector and the area vector. That's 90 degrees. Well, if you know your cosines, and I know my cosines, I think, hope. I mean, actually I have a problem, I say that. I have a problem with cosines and sines, like the problems with left and right, like the problems with the plus and minus. There's some sort of problem with that. But anyway, cosine of 90 degrees is 1. No, cosine of 90 degrees is 0. I've got the problem. And so, because these 2 vectors are perpendicular to one another, this flux is 0. And so that was actually a simple calculation. We could have seen it, just visualized it, that no field lines would pass through that surface, but we showed it mathematically that that flux is actually 0. And actually, the same is true. I won't write out the equation. The same is true for the bottom. Again, E and A are perpendicular. And also the front and the back. All those 4 sides have E and A perpendicular. All those 4 sides have 0 flux through them. So that was pretty easy. We've done, 4 out of the 6 faces without much work. Let's do the 2 other faces. They're a bit different. So let's do the right face. So that's the one over here on the right. If I was to picture it a little more carefully, it's kind of here. And let's figure out the flux through that. So in this case, the vector E is still towards the right. That's not going to change. But now the vector A, which is perpendicular to the surface, is towards the right. So they're parallel to one another in this case. Now I should say an important point about convention about closed surfaces. The vectors A, the area vectors A for a closed surface, by convention, point outwards from the inside of the closed surface to the outside world. So this vector that's for the right-hand surface, and also I did it for the vector for the top surface, is pointing out of the box to the outside world. So the right surface vector A points towards the right. So picture that there, and then we can calculate the flux as E, A, sine, gosh, I told you I have this problem. Sine 0 degrees, so cosine 0 degrees, and we just got to calculate this. So cosine of 0 degrees is 1, and therefore this is just E times A, so 500 newtons per coulomb times the area of the surface is 1 centimeter by 1 centimeter. So that's 1 square centimeter. 1 square centimeter, I better put it in SI units, is 10 to the minus 4 meters. It's 0.01 meters times 0.01 meters, which is 10 to the minus 4 meters. So I've got 10 to the minus 4 meters times 500 newtons per coulomb. That comes out to be 0.05 newtons meter squared per coulomb. And so that's our electric flux through the right surface. We've only got one left to do. We've got to do the left surface now. So for the left surface, the electrical field is, again, towards the right. The area vector is towards the left. It's perpendicular to the surface and pointing out of the box. So it's in the opposite direction. So then the flux is going to be EA cosine 180 degrees. And the cosine of 180 degrees it's not plus 1, it's minus 1. So this flux is going to be, it's the same strength field, it's the same size area, it's going to be the same size flux, 0.05 newtons meter squared per coulomb, but it's going to be negative. So this is minus 0.05 newton meter squared per coulomb. And that's in comparison to the right face, which was positive. So negative flux is sort of coming in through the left-hand face, positive flux going out through the right-hand face. If I want the total flux through the entire surface, so this is through the entire cube. I'll put a little cube on here. Nobody can read it, but I will do it. And nobody can read it because I've gone off the page. That flux is going to be 0 plus 0 plus 0 plus 0. Those are the top, bottom, front, and back faces. Plus 0.05 minus 0.05 for the left and right faces. All add up to 0. So actually, there's no net flux through the entire box. There is a flux in and out through the left and right faces, but they perfectly cancel one another out. And actually, that result for the cube is true for any closed surface in a uniform electrical field. So supposing I put a sphere in that uniform electrical field, it'd be mathematically hard for us to compute the flux through that sphere, but the net flux would be 0. And a way you can visualize that is that every field line that went in the sphere would come out the sphere. If I put a weird blob-shaped object into a uniform electrical field, again, it would be mathematically impossible for us to calculate some general weird-shaped blob flux in that uniform electrical field. But every field line that went in would come out the other side, and so the net flux would also be 0 for that arbitrary shape. Okay. Now I want to talk about Gauss's law. And Gauss's law is actually a partner to Coulomb's law. It's very interesting. There are two different ways of expressing ultimately the working of the electrical force in terms of electrical fields. So you might know Gauss. Obviously you don't actually know Gauss, but you might have heard of Gauss because he was tremendously important in mathematics and physics, especially in mathematics, but also in physics. And Gauss's law is due to Carl Gauss. Okay, here's the law. Enough history. So up here is a sentence that describes the law in words. And downstairs here is an equation that describes the law as an equation. And here is a picture, a sketch, that describes the law as a sketch. So all three ways of describing this law. What does the law say? The law says, think about closed surface. So it's only about closed surface, it's not about open surface. It says that the electric flux through a closed surface, the net electric flux through a closed surface, like what we just calculated for the cube, is proportional to the amount of charge inside the closed surface. So if there's more charge inside the closed surface, there's more flux through the surface. If the charge inside the closed surface is positive, you'll get a positive flux. If it's negative, you get a negative flux. If there was no charge or no net charge inside the closed surface, there would be no net flux, no total flux through the closed surface. So it's a very fundamental idea. That's the sentence. Here's the equation that describes it. So the important thing in this equation, firstly, is here's the flux through the closed surface. That's the phi. And Q in this equation, you see it here in this version of the equation, over here on the right in this version of the equation, Q is the charge inside the closed surface. So first of all, it is just a statement, again, that the flux through the closed surface is in proportion to the charge inside the closed surface, but it's telling you what the coefficient of proportionality is. What is the proportionality between the flux through the surface and the charge in the closed surface? You can write it in terms of the Coulomb constant that we've already met. So you can write the flux is equal to 4 pi times the Coulomb constant times the charge inside. Or alternatively, sometimes this is more convenient, you can write it, that flux, as the charge inside divided by a new constant. It's called the electric permittivity. It's written as epsilon naught. It's, related to the Coulomb constant. And this is a second way of writing the flux law in terms of this electric permittivity instead of this Coulomb constant. It's the same idea, same equation, just two. We just have two, for some historic, ridiculous reason. We had two different constants that basically just characterize the strength of electricity. Okay, so here's a way of visualizing it. So imagine that sheep were charged. Every sheep carries an electric charge. Some of them are negative charge, some of them positive charge. Some of them have big charges, some of them have small charges, but sheep are charged. And then imagine a pen containing the sheep. A sort of closed pen containing the sheep. The electric flux due to the electrically charged sheep through that pen is determined by the sheep that are inside the pen and not the sheep that are outside the pen. So the point of this picture is that the flux through this pen here is determined by this sheep here, because he or she is inside the pen. It's not determined by this charge here, this sheep here, because he or she is outside the pen. So the in here, charge in, is charge inside the surface, and that's very important. So when you calculate the flux through the surface, you only account for the charges inside the surface, and you ignore the charges outside the surface. They do contribute flux over patches of the surface, but it cancels out. They make no net contribution to the flux through the entire closed surface. So it's very interesting to me. Okay, let's show a demonstration of it. This is a demonstration that I personally invented. And what we're going to imagine is that this is a charged cylinder. So this cylinder here, say, has 1 coulomb of charge on it. And therefore, it's surrounded by an electrical field. And as we've seen, it's a source of electrical flux. if I put that charged cylinder inside this closed surface, it's like the sheep inside the pen, the flux through this closed surface is that charge, it was 1 coulomb I said, divided by epsilon naught. Or that charge times 4 pi times the Coulomb constant. That's the flux through the closed surface. Very easy to calculate that flux through that closed surface with Gauss's law. If I take that charge out, and I just lay it on top of the surface, the closed surface, then the flux of this 1 coulomb of charge, net flux through this closed surface, now it's 0 because it's not inside the closed surface. And so you can calculate the flux through closed surfaces very straightforwardly by just knowing what charge is inside, what charge is outside. Ignoring the charges outside, accounting for the charges inside. That's Gauss's law. Okay, where am I going? I wanted to show you that the new Gauss's law and the old Coulomb's law are actually related to one another. And it's easy to show that they're related to one another by calculating the flux, the electric flux, through a spherical closed surface, that's this dashed line here, that's centered on a single positive charge. And so we're going to calculate, if you look at that picture, we've got a positive charge in the center, point charge in the center, creates an electrical field. I've sketched the electrical field lines. They're coming radially outwards because it's positive charge. The field strength gets weaker as the inverse square of the distance. That's Coulomb's law. And we're going to calculate the flux of that field through that spherical surface that's what I would call concentric or centered on that positive charge. And so that's our job here. And we're going to use our understanding of electric flux and its relation to electrical field to make that calculation. So that's what I want to do. Okay, so supposing I want the flux through this surface here. I mean, it's in cross-section here. This is just a circle, but it's actually spherical. And I called its radius r. To calculate the flux through this surface, well, what are the ingredients in flux? There's the electrical field strength over the surface. So I'm going to need that. There's the area of the surface. I'm going to need that. And I also need to know the relative orientation of the field to the surface. I'm going to need to know that. And so those are the three things I've listed over here. Electrical field strength. Well, it's just a point charge. The surface is a distance r from the point charge. And so the electrical field is just k times q divided by I squared. That's the field of a point charge at a distance r from the point charge in terms of the charge q. So hopefully that's straightforward. That's last class. What's the area of the surface? Well, that's, the geometry that we did in middle school. I missed some of that, but I do remember that 4 pi r squared is this surface area of a sphere. And so this sphere, radius r, has an area 4 pi r squared. And then finally, we need to think about the relative orientation of the surface in the field. You could think about it by thinking about some location on the surface. You could think about the top, say, or over here on the right, or anywhere. But let's think over here on the right. The field is pointing towards the right. The area vector that represents the surface here is also pointing towards the right. It's pointing out from inside to outside, the closed surface, and it's perpendicular to the surface. And whether you think here, or you think upstairs here, or downstairs here, or anywhere else about the relative orientation of E and A, they're always parallel to one another. A is always pointing away from the point charge, out of the surface, and E is always pointing radially outwards from the point charge. And so, finally, E and A this means parallel everywhere. So why did I put, after all that, why did I put 90 degrees? This is a typo. I'm going to have to correct this. So to calculate the flux, we've got to multiply E, A, and cosine of 0 degrees, not 90 degrees. That's wrong. This is 0 degrees. E is kq over r squared. A is 4 pi r squared. And cosine of 0 degrees, not 90 degrees, is 1. When you multiply these three things together, the r squared in the denominator here and the r squared in the numerator here cancel. You're left with a k, a q, and a 4 pi. We're left with 4 pi kq. And this is Gauss's flux law. And so that you see here, I mean, it didn't help that I wrote 90 degrees instead of 0 degrees, especially after that entire discussion about that I do this all the time. But anyway, we've seen, the big picture of this is that out of Coulomb's law has emerged Gauss's law. Like Gauss's law is inside Coulomb's law. And you can also think of Coulomb's law as being inside Gauss's law. They're just alternative perspectives, viewpoints on how electricity works, how electrical forces work. And sometimes one's appropriate for a particular type of problem, sometimes another one is appropriate for a particular type of problem. That's why we have these two versions. Okay, let's look at an example of Gauss's law. I've got a couple of kind of qualitative ones, and then we'll look at a quantitative one. So here's our point charge, plus Q. And here's in tangerine, the surrounding electrical field. So we're seeing the field lines. We're seeing the field is strong near the charge, weak far from the charge. We're seeing the direction of the field. It's radially outwards. And then we're seeing three closed surfaces. This one horseshoe shape. This one labeled 2 is, say, a sphere. And this rectangular one here labeled 3. So there's three surfaces in this field. Now, again, I'm drawing these surfaces in cross-section. They are closed three-dimensional surfaces. That's important. They have to be closed surfaces for our argument. So what is the flux through each of those surfaces? Well, the flux through each of those surfaces is actually 0. They are in an electrical field. So they are in that electrical field of that positive charge. It's in the neighborhood of those surfaces. It's creating field that passes through those surfaces. But the net total flux through those surfaces in each case is 0 because that charge is outside of those surfaces. It's not inside those surfaces. So when you calculate the net flux through a surface, it's determined by the charge inside the surface. It ignores the charge outside the surface. They contribute nothing to the net flux. So you can see how that works if you look at these three surfaces. If I look at this horseshoe-shaped one, field lines are going in on this inner wall. So these field lines is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? Well, there's a lot of them that go into this surface, but they all come out. Look, it's coming out over here on the right, they're coming out upstairs, they're coming out over here on the left. So they all come out. That means that there's no net flux in or out. Same thing for this spherical surface over here on the right. This field line goes into it, but it comes out of it. There's no net flux. Same thing for this one downstairs, this rectangular surface. There's a field line that goes in, but it also comes out, so there's no net flux. So that's a very powerful way, and a very sort of visual and quick way of understanding electric flux through the surfaces with Gauss's flux law. What counts as the charge inside and not the charge outside. Okay, this is a quiz question. So let me publish this. So you should see this now on canvas. And it's asking a similar question: what is the net flux through three surfaces? They're now labeled A, B, and C, that are in the environment of an electrical field and in the neighborhood of electrical charges. And so you've got to compare the fluxes through these different surfaces. So I'll give you a couple of minutes to think about that. Okay, I'll get started with the solution. So again, the key idea is, if you want to know the flux through these surfaces, A, B, and C, is to think about what charges are inside those surfaces. So for A, and also for B, you look at the sketch, the positive charge is inside A, and the positive charge is inside B. The negative charge is outside A, and it's outside B. I hope. So A and B have positive charge overall inside them. And so they will have a non-zero positive flux through them in proportion to that charge. C, on the other hand, C contains the positive charge, but also contains the opposite sign negative charge. So C has overall one positive, one negative charge, a total charge inside it that's zero. So since the total charge inside C is zero, there's actually zero flux through, zero net flux, zero total flux through surface C. So the correct answer is that A and B do have fluxes through them, but it's non-zero. C has zero net flux through it. Okay. Here's a more quantitative example of electrical flux. So let's see if we can solve this particular problem. So in this particular problem, we're told that a 1.6 nanocoulomb charge is at the center of a shape called a tetrahedron. So a tetrahedron is a volume that's made of getting this wrong now, 4 equal triangles. It's actually, I tried to make a joke with the pyramid, but that's a really bad joke because it's not a pyramid. No pyramid has just 4 triangular shapes to it. They have 4 triangles and then a rectangular base. So this is actually not a pyramid. It's a tetrahedron that's made out of these 4 triangle shapes. So there's one over here on the left, one over here on the right. There's one which is the base, and then there's one hidden is the back. So there's the 4 triangles. And so we're asked to figure out a couple of things. What is the electric flux of that charge through the entire surface? And what is the electric flux through just the surface of one face? And so let's do that calculation. I'll do this on the document camera. Okay, so here's my question. What's the net flux through the tetrahedron? I'm going to answer that. And then also I'm going to answer what is the flux through each of the surfaces, the 4 surfaces of the tetrahedron. So to find the net flux through the tetrahedron, I'm simply going to apply Gauss's law. And if you remember, Gauss's law is this equation that the electric flux is 4 pi times the Coulomb constant, K, times the charge inside the distribution, inside the closed surface. So importantly here, right, this tetrahedron is another closed surface. The combination of those 4 triangular faces make a closed surface. There is a definite inside and outside. You can't get inside if you're outside without walking through a wall and vice versa. So we know the charge inside. It's 1.6 nanocoulombs. To calculate the net flux, all we've got to do is multiply the Coulomb constant by 4 pi. So Coulomb constant is 9 times 10 to the minus 9 plus 9. Gosh. Newtons meters squared, Coulomb squared. Got to multiply that by the amount of charge that we've got. We've got 1.6 times 10 to the minus 9 nanocoulombs. Am I still on the screen? No. And calculate this product. So look, the 10 to the 9 here and the 10 to the minus 9 here will actually cancel out. So we could just do 4 pi times 9 times 1.6. And if you calculate that, that comes out to be 181. 181, the units you can see here, is the units of the Coulomb constant, but it's multiplied by Coulomb, so 1 Coulomb of the Coulomb squared in the denominator is cancelled out. Here's our units. And so that was easy to calculate the flux, net flux, total flux, through that tetrahedron surface. What about the flux through each of the 4 faces? Now, we can do that in this case because we were told that the charge is located at the center. That means that the charge is the same distance from each face. So each face of the four faces sees the same view of the charge. So it's kind of what I would call a symmetry. There's a symmetry of the geometry if we place the charge at the center. Each face is the same distance from the charge. Each face will see the same kind of electrical field pattern. Each face will share equally the electrical flux. So in this case, if I want the flux through a given face, the idea that's letting me solve this is kind of the symmetry of, it sounds like a movie title, symmetry of faces. So it's that feature of this arrangement that allows me to just say that the flux through one face is equal to the total flux divided by 4, because there's 4 faces. And so 180 divided by 4 is 45. So it's about 45 Newton meters squared per coulomb again. And so that's the answer to the flux through each of the 4 faces. If the charge hadn't been at the center, so suppose the charge was off-center, how would this problem change? The flux through, the net flux, the total flux through the entire tetrahedron, that would be exactly the same. There'd be no difference. But if the charge wasn't at the center, we wouldn't have been able to answer. It would be impossibly complicated to answer what is the flux through each individual face. It would be different. You know, a face that's closer to the charge would see more flux. A face that's further from the charge, less flux. But to actually calculate those fluxes would be impossible. It's only because it's at the center there was a symmetry. Okay. Last class, as usual, ran out of time, and I didn't cover that last slide on the electrical fields in the presence of conductors. So I want to show you that slide, and I want to show you a problem that involves the concept from that slide and electrical flux and Gauss's law. So there are some special rules about electrical fields when you have conductors. So if you have remember a conductor has inside it what I would call mobile charge carriers. That's charge carriers that can move around. Charge carriers that can flow around inside the conductor. They'll flow around or move around under the influence of electrical fields. When a conductor is in what we call non-equilibrium, what that means is that there's an electrical field inside the conductor that's causing the charges to flow around, move around. They're rearranging themselves. When the conductor reaches what we call equilibrium, that's actually when there's no electrical field inside the conductor. They've ran around, rearranged themselves to cancel out the electrical field. And so it's that latter case, a conductor in equilibrium, that I want to discuss the electrical fields. It's that latter case when electrons aren't moving around, charge carriers aren't moving around in the conductor, that I want to mention the electrical field. So there's 3 rules, I've listed them here, about an electrical conductor in an electrical field. The first rule is that in equilibrium, the electrical field inside the volume of the conductor is 0. So that's an important rule. If the conductor's in equilibrium, the electrical field inside is 0. The second rule is that if a conductor is inside is immersed in an electrical field, once the conductor's at equilibrium, the electrical field at the surface of the conductor is perpendicular, right angles to the surface. Those two rules apply in equilibrium, okay? If the electrical field wasn't zero inside the conductor, then the charges would still move around, so it wouldn't be equilibrium. If the electrical field wasn't perpendicular to the surface, then the charges would move around over the surface. It wouldn't be in equilibrium. So kind of by definition, equilibrium of the electrical conductor involves zero electrical field inside the body of the conductor and perpendicular electrical field at the surface of the conductor. In that way, there's no movement, no motion, no flow of the charges inside the conductor. There's one other thing about a conductor in equilibrium, one other point about a conductor in equilibrium. So there can be regions inside the conductor that are positively charged, i.e. have more protons than electrons. There can be regions that are negatively charged, so you have less protons than electrons. But those regions are limited to the surface. They can only occur on the surface. So if you could imagine you could swim through a slab of steel. Right? Imagine that. Well, inside the volume of the steel, if it's in equilibrium, it will be electrically neutral everywhere. Overall, electrically neutral everywhere. Equal numbers of electrons and protons. But at the surface, you could find regions that were positively charged, regions that are negatively charged, where there's excess protons or excess electrons. And so that's a feature of conductors in equilibrium. Here's an example. Let me show this example. This conductor in blue is immersed in some electrical field. This conductor in blue is in equilibrium in that electrical field. That means that inside this conductor, the electrical field is zero. That's what I denoted here. E equals zero inside. That means that at the surface of the conductor, here's one location on the surface, but there's lots of locations on the surface, the electrical field is perpendicular to the surface. This is a right angle. And finally, it means that any regions of excess charge, and there are in this case, are located on the surface of the conductor. These regions of charge are where these field lines are ending, and they're all right on the skin of the conductor, right on the outside surface of the conductor. They're not in the volume. They're not in the body of the conductor. Okay. So this is an example problem that involves Gauss's law and this concept of conductors. And in this particular problem, we're told that there's a charge positive Q in the center here, and it's surrounded by a conducting hollow sphere. So in gray here, imagine this is some manufactured in the basement, some sphere of steel that's hollow inside, got this wall to it, and I put inside that a positive electrical charge right at the center. And the question asks, what is the field in this region? This is inside the steel shell. What is the field in this region too? This is within the steel itself. And what is the field in this region? Outside the steel shell. And so this is a famous problem that we always show in classes on electricity and magnetism when we're thinking about Gauss's law and we're thinking about conductors, because it's a great illustration of your thinking, your understanding of Gauss's law and conductors. So we're going to find the field in these three regions. And the way you do it, the way you solve this problem, is to imagine starting in the center with the positive charge and walk your way out through the three regions, 1, 2, 3, from that interior region to standing in the steel itself to getting outside the sphere. Okay. So what's the field inside the sphere? Specifically, I'm going to write down an equation for the field at a distance r from the positive charge that's inside the sphere, within the inner radius of the sphere. So to figure that out, I'm just going to use Gauss's law. This arrangement of the steel and the charge has a spherical symmetry to it. Looks the same at the top, the bottom, the left, and right. There's a spherical symmetry to it. You could rotate it, and it would look exactly the same. If the charge distribution has a spherical symmetry, it actually means that the field must inherit that spherical symmetry. So the field, whatever it looks like, is spherically symmetric. So if I put a closed surface inside the sphere here, I can figure the field at the closed surface using Gauss's flux law. And I can do that because that field, I don't know immediately the strength of that field, but it must be uniform over that closed surface. And so if I turn to Gauss's flux law, look, here's Gauss's flux law. Flux equals 4 pi k, the Coulomb constant, times the charge inside. I'm going to apply it to this surface here in magenta. The flux will be the electrical field that I've argued must be uniform, the area of the surface is the area of a sphere, times the cosine of the angle between the field vector and the area vector. The field, because it's a positive charge, must be coming radially outwards. The area vector is just the pointing radially outwards from the closed surface, so that's 0 degrees. And so I can calculate the expression for this field by just filling in the area vector, size of the area, 4 pi r squared. I get this little expression here, and rearranging for the electrical field. So inside, despite the iron or the steel shell, the field inside looks just like the field of a point charge. And we figured that with Gauss's flux law. There's 3 regions here. I'm just going to do the second region because of time. There's the third region in the slides. And I also got a video on this one. But let's just look at this second region. This is now inside the shell. What's the field inside the shell? Well, in equilibrium, this conductor, the field inside that shell, is going to be 0. That's the rule. So that field is actually everywhere in here. We've nulled out the field of this charge by to create 0 electrical field inside the shell. What the electrons did inside the conductor is they moved around to accomplish that. Electrons collected on the inner surface here. So this is negatively charged. We can have a negatively charged inner surface. And if this is negatively charged, there must be an equal quantity but opposite sign of positive charge on the outside. So there's positive charge smeared over the outside.